My name is Fabio Stroppa. I'm an assistant professor at Kadir University in Istanbul, Turkey, and I'm also the head of EvoLab. So these are some videos linked to my IROS submitted papers, which will be presented later this week. They are both on soft-growing robots, which is the main topic that we work on in the hardware side of my lab. This is something I started working when I was a postdoc at Stanford with Professor Alison Okamura, and I was very interested in this robot because they are different. They have this new type of degree of freedom, which is eversion. They can grow and they can retract. So the kinematics chain is different. It's interesting. The first work, which will be presented on Thursday, is about motion planning for the specific kinematics of the robot that we proposed. So what we did, the interesting part of this work is that we adapted a discrete graph-based algorithm for motion planning, A*, to be working on these continuous scenarios. It's not something that you usually do because there are huge limitations on these discrete algorithms. However, we made it work with some assumptions. Of course, these assumptions then evolved over time, and right now we have made new assumptions. Once we have the real robot that works, we have different type of actuations, and we have more considerations. So we in the meantime, this was published 1 year ago on Robotics and Automation Letters, and now it's presented today at IROS. But in the meantime, we also developed different other algorithms to a more optimized version. The paper is currently under revision. But if you want to know more, please come to see us on Thursday. We will be happy to answer your questions. The second work that we present is about designing a perfect robot in terms of the link lens. So what are the link lens that you want to build, that you want to construct for the robot to perform the specific task you're looking for? So imagine you have targets, the stars that you can see here in the example, and some obstacles, those circles, and then you wanna have a robot that can reach all the targets by avoiding all the obstacles. So this is a software that we made years ago, but then there were some considerations that we didn't do before. So we thought, what if the robot, instead of just touching the targets, actually has to carry the targets, because there are different modalities in manipulation tasks. So for example, if you want to get to the target and then carry it around, then we have to make sure that the robot, the target doesn't get stuck between two obstacles. So that changes the optimizer in a way that the robot cannot just go straight to the target by simply avoiding obstacles. It also has to take into consideration where the target is stuck. And there are different modalities that we discuss. There are 6 modalities. If you want to know more, please come on Tuesday during the session, and we will be happy to answer your questions. Thank you. I wanted to show you some of the recent achievements and latest publications in the last 2 years in my lab, EvoLab, in Istanbul, Turkey. And all these works are mostly related to soft-growing robots, but not only. We also have other interesting works on drones and exoskeletons, and also haptics. So related to soft-growing robots, this is the first project that I actually got as a PI. It's based on optimizing the design of a soft-growing robot for a specific task. So let's say that you have targets around in the environment, you know their position, you know that you want to reach them with a specific orientation, and probably there are obstacles on the way. So what are the lengths of each link that you need to build for a robot such that it retrieves all the targets? So this is done basically by an inverse kinematic solver with an evolutionary algorithm or a genetic algorithm. And it consists of solving different constraints, different objectives, and so on and so forth. We also have a 3D version, which is still under revision, so the paper is not published yet, but you can read it from archive, or you can download the software, both softwares. Those are different softwares. So it might take some time before this gets published. Related to this, once we have a design, an optimized design to reach target 1 and reach target 2, then we also need to move from target 1 to target 2. So we need a motion planner. This work actually will be presented on Thursday here in this venue, although it was published in IEEE Robotics and Automation Letters. And it's based on a motion planner with A*, which is something weird. It's unusual. It's not something they usually would use to solve this kind of problem. So that's why it's interesting. We already have, we are working on new algorithms. This is already outdated, unfortunately, but that's how research moves on. So I invite you to come on Thursday to check this out and maybe talk to me and my students. Moving on from soft robots, we also explore different kind of things. This is related to haptics, so not really robotics, but maybe some of you in the audience might relate to this. It's an interesting topic. So the idea with this is that how can we improve the performance, or not just the performance, but the interest of people doing user studies by gamifying the user study itself. So we thought that we had actually an application in which we were monitoring the reaction time of people while visualizing some cues and pressing a button, also stimulated with haptics. And then we thought, this kind of looks like the famous whack-a-mole game, as you can see from the screen. So we decided to gamify it and compare the results. And although there are some differences, with this paper, we realized that gamification actually helps at least the excitement for the task. So we can gamify user studies, although there are differences, and now we are currently testing why are those differences, what is the point of those differences? Maybe they are cognitive, or maybe it's just hardware, so there is a delay in the rendering of the environment. So we're gonna see what else comes up with this. This was presented also this year in the World Haptics. Let's go back to robots. This is another work that we got published this year. It's about optimizing the design of exoskeletons for rehabilitation. Once again, with evolutionary algorithms. My lab is called EvoLab because we mostly do software, but applied to robotics. So we use the evolutionary algorithms, which is like a very common tool at the disposal of engineers to optimize their work. However, while we were studying the literature, we realized that not many works actually do a proper job in optimization. And in fact, the kinematic model of this robot was made by one of the co-authors over 10 years ago, and it was optimized with simple brute force. So we decided to step in and improve the situation to have a more optimized robot. We were able to obtain a design that maximizes forces, so the torque, also balances these forces on the finger so that it's not dangerous, so the finger doesn't snap, and also the length and the size of the actuator. Maybe we can buy a smaller actuator, which would be cheaper. So all these objectives were optimized in order to retrieve the best design for this robot. Then last but not least, we also worked on aerial and ground vehicles, or drones. This was actually accepted yesterday at the time of the recording, so today you probably can already access this paper, but we don't have I didn't have the link by the time I recorded this video. So the problem here was so we have a set of drones scanning an area, but at a certain point those drones will run out of battery. So they have to meet up with some ground vehicles on the ground. They're running on the road, and they carry the charger. They can charge once they meet up. So the idea was, how do we plan the mission such that all the drones and all the ground vehicles communicate with each other to minimize the time of the mission and make sure that they don't run out of battery. And to the best of our knowledge, this is one of the few works, there are very few studies that address this problem, especially when there are multiple aerial vehicles, vehicles and ground vehicles, unmanned aerial and ground vehicles. So this was the very latest paper that we got in, and it's an exciting work. So this is just a few, the latest that we have. We have more cooking. This is a photo of my team, not even all of them. It's hard to organize a picture with when you have more than 30 students around. This is me, if you were asking, if you're wondering. Thank you very much for having me. I'm really excited to be here, and I can't wait to talk with you.